So today I'm going to be talking about the work that we do at JBP. Myself, and I've also got my colleague Zoe up here who does a huge amount of work for us, but she's unfortunately based in Brisbane, so couldn't come today. About harnessing GIS and our free open source software to enhance flood risk assessments. So who we are as a company, this will give you a little bit of background in terms of why I'm talking about this and kind of the data I'm showing. So JBP is part of a big kind of group called JBA. We're a flood and climate risk management consultancy, and we specialize in kind of multi-agent resilient projects, but we mostly focus on flood risk. And particularly we work with a lot of kind of collaboratively with a lot of international institutions, governments and humanitarian organizations. And this means, unlike mining companies, they don't have a lot of money. They don't have that data availability either, so we need to really make sure that we can source any sort of free data for them to kind of help them make decisions in terms of kind of risk management or prioritizing key assets and infrastructure. We're based both in Perth and Brisbane. I opened up the Perth office last year. Here we kind of look at kind of statewide risk mapping, so that really large scale things like asset resilient assessments, like I said, and kind of forecasting systems and kind of disaster response, so taking any sort of input data and then kind of getting kind of impact forecast for people. So we're pretty lucky as a company. We actually have global flood maps around the entire world of river, surface water and storm surge, which we've just released. So unfortunately these aren't free and open source, but we do often sell them for quite cheap to kind of community organizations. We have these at 30 meter resolution around the entire world and 5 meter resolution in kind of Europe, US, and also in the kind of the major cities. And what's really important when we're looking at kind of these flood maps, if you're ever going to work with them or doing risk assessments, is that we have a bunch of return periods. So for ours, we have 6 return periods. And for those of you who are not familiar with this concept of a return period, in flood risk assessments, the return period indicates the likelihood of experiencing a flood of a large magnitude within a given time frame. So what that means is if you've got, someone says, this is a 100-year flood event, that means it's an event of a particular size that has the probability of occurring in a 1 in 100 probability of occurring or a 1% probability in any given year. So we've got our 20-year flood return periods. That would be the probability of occurring 5% of the time in any given year. So that's kind of a smaller flood. And then we get out to our larger years, like our 500-year and 1,500-year, which is really big. So why is this important? And when we're looking at kind of risk assessments, communities, whether it's kind of planning or even kind of insurance companies, they want to be able to build the infrastructure to withstand a certain flood. So most houses these days, they need to be able to withstand a 100-year flood. So that's pretty big. So again, that flood that's got a chance of occurring 1% of in any given year. If you're looking at things like hospitals or some kind of sort of critical infrastructure, we really want that to be more like 200 to 1,000-year flood. And if you're looking at something where, say, it's the Department of Defense, most military installations, they want to be able to withstand a 10,000-year event. So that's pretty significant. So they want to be operating in terms of huge flood extents. So how do we enhance those kind of data sets, so our flood maps, when we're looking at our flood risk assessments? So we're looking at doing things like, for example, for councils, if you've got property data sets, you can look at council-wide depth damage assessment. So, what's the depth of flooding for a given return period, how many damages you're looking at, so they have an idea in terms of if they need to go and get disaster funding, how much do they need to apply for the government. For transport networks, how long are they expecting a closure if you've got a big event coming through. What are the write-off losses if it's an insurance or reinsurance company. And particularly what I'm most interested in is kind of infrastructure resilience planning and prioritization. So what's your kind of population at risk, where is that, what percentage of your local government association, things like, how resilient are your hospitals if we have a big flood, can we even use your hospital, do you need to start looking at upgrading that? And the last bit is you can really start bringing in any sort of environmental data sets into this as well. So you can have a look at, say, where are the locations that we can start growing more mangroves or vegetation to improve that assessment. And this all initially happens on that really large scale, because it's not a local council that's necessarily making a decision. It's really the state and federal governments or larger organisations who are putting money into that. How we do it, obviously, like everyone, we use QGIS. About 6 or 7 years ago, our entire company of about 700 people stopped paying ARC and moved to Q. It's a fantastic piece of software. So we use that for all our spatial assessments. And we also are looking for consistent data sources across the entire assessment. So this is really, really important, and I can't stress it enough. If we're assessing, for example, local government areas, we want to have a statewide data set, because we can't compare, for example, the City of Canning, really great work that they've done there in terms of upgrading their pathways. We can't compare that to, say, another council who's done nothing, because then when we're comparing those two councils together and we're telling the government, Canning's at a huge amount of risk because they've all got these assets, we're then going to be underestimating the risk for any other community. And again, if we're assessing country versus country, then we'll start using global data sets. So that's when we'll use things like Bing Maps or anything from the kind of World Health Organizations that we can get, or anything globally like that. So like I said, if we can't find consistent data sources, you just really need to be aware of any potential biases in those risk profiles. So when you're doing that analysis, it's really important to note that down for the client, because clients will obviously, you'll provide a map, and they won't necessarily think about it any further. So it's really important to kind of note that down, because we're not just kind of spatial analysts. We really need to pass on the knowledge that we have, because we're often far more knowledgeable than our client. So what I'm going to do is just go through a quick example approach for Western Australia. This is just using what we find the best data here. Again, if you've got any questions in terms of other states or around the world, happy to kind of chat to you afterwards. So in WA, the best available data is pretty much on the WA website in SLIP. You can get things like the LGA boundaries from the Department of Transport. They also provide road network, rail crossings. They're generally pretty up to date. They're probably within 3 years. Again, note that down in terms of when you download that data, how new it is. Get hospital locations from the Department of Health, fire stations from DFES, and then building footprints we get from DPIRD as well. So that's just residential buildings from those. And then we also get the ABS census data, and that's really important in terms of making more, getting kind of more information and building on statistics to provide to any clients. So what does data look like around WA? Obviously it's pretty big. You can see both hospitals and DFES fire stations. Really focused around the southwest, much like anything, huge amount there. Again, it's kind of data sources there if you want to see them. Again, you can get rail crossings. This is important because if we flood rail crossings, that's going to stop your road network and also stop any kind of goods coming into WA. And you can see buildings as well. What we found is depending on what open source building shapefile you use, you'll get kind of a big variation in terms of the number of buildings. So for example, if you're using Bing, that might only give you, say, 50% of the buildings that are actually there. Vice versa, obviously they're updating it every time. But before we can use this data in any of our assessments, we have to be able to ground truth it and really be happy with it ourselves, because we're the ones who are providing that. Yourselves are the ones who are providing that information to any clients. So in terms of extracting meaningful statistics, once you can get all the data you have, what you want to do is intersect your flood maps in terms of extent and depth with all your kind of collated data. What we tend to do is we tend to rank for risk. So we're intersecting, obviously WA is pretty big, so we take the local government areas and we kind of subdivide the state, because it's too much to be able to process that all on our computers unless we go onto our larger computers, which are used for hydraulic modelling. So we'll kind of subdivide the state, and for each general area, we'll do all the calculations, bring it all back together, and start ranking risks. So, for example, you might do things like I've got up here, most buildings impacted, percentage of population impacted, greatest length of road inundated. You can have greatest length of railway, just overall how much of your LGA is going to be inundated for a given event, a given flood. How many hospitals are at risk of inundation for different floods, and same with that number of your DFES stations. It's not very helpful if all your kind of emergency response stations are flooded, and you need to get them out. So this is, for example, a breakdown looking at the number of buildings per LGA. So this is just with the base DPIRD data. So this is an example, and then on the right you've got a table there showing the top 10. So that just gives you an idea of how many buildings per local government area. And then we can start intersecting that with any of our flood maps. So this is looking at the percentage of buildings at risk of flooding in a 100-year event. So this is, again, just one of those magnitude flood events. But we do like to use that over each time. And what you can see if I flick between the two is, this is the number of buildings. So if you just looked at kind of infrastructure that's there, you might think Stirling's actually the the most at risk. Once we intersect that with our flood extent, suddenly you see Mora, Murray, Beverley, York, they're all kind of appearing, there's a lot of places that are somewhere between a 25 to 30% risk of flooding in a 100-year event. This is important because you can give this back to the state and they can start kind of allocating their funding and think about should we really be supporting certain areas of the state. Again, fortunately, I was quite happy about this one. A number of hospitals flooded in a Q100 event. So fortunately, there's only 5 locations with 1 hospital flooded. So that was nice to see. So not too many, but still, it is a little bit of a concern if there's only a few hospitals there. So for something like this is where you might look at that and you might want to go into more detail and have a look. How high is the hospital? Do they have any sort of resilient measures in there? What other information can we get? Number of DFS stations flooded in a Q100. Maximum was 5 in Wynnum, Kimberley. So obviously they're a little bit of a strife if the cyclone hits. They won't have any fire stations to kind of rescue anyone. But again, pretty low numbers, so that was good to see. When you go over to the east coast to say northern New South Wales, you actually, for example, find half the fire stations will be flooded during an extreme event, which they're getting kind of increasingly more. And how to kind of build on this data is you find data sets out there that you can kind of enhance any of those statistics. So we're looking at taking that spatial data and then combining it with anything else we can get. So this is an example for population at risk, so it's using ABS census data. And what you can get out of that is every single LGA will have the median number of people per household. So you can go through and multiply your median number of people by the number of homes you have, and you can come out with a kind of, again, statistic, what's the population at risk, and you can be plotting that up. So you can see when we do it with Canning, this is kind of a combined risk I'm showing you here, and you can see the City of Canning has the largest population at risk during a 100-year event that could occur, followed by Murray, Collie, again, Wynnum, East Kimberley as well. And you can see Perth in there as well at number 7. So, but not too many people at risk during a 100-year event, fortunately. So you kind of intersect all these data sets you have, and you have a risk for each one. So we've got risk of buildings flooded, risk of population, risk of hospitals. And the next step you want to do is you don't want to give 20 maps to someone because that's a lot of information to digest. So you have to start thinking as an analyst, how am I going to combine these together? And so we can create just one single map. So again, all done in kind of QGIS. When you're combining the maps, you want to make sure we're not double counting. So for example, you won't combine buildings and population at risk because you use the buildings shapefile to calculate your population. So if you combine those two together, you'd almost be weighting that as 2. It's more important than, say, hospitals at risk or fire stations. And what you combine will really depend on what that person's interested in. So you can combine them all together, and you see what comes out on top. We've got Mora as the most at-risk LGA in a 100-year event. Followed by Murray, Beverley, York. And I think recently there was an article released by, I can't remember what insurance company, that essentially rated Murray and Beverley combined as the highest risk LGA to flooding in WA. So I think it was in the top 10 in Australia. So you can see these kind of statistics, they come out quite well. Obviously, Mora didn't feature quite highly, but again, they combine their risks in different ways. And you kind of see that when we have a look at this combined exposure. So again, we can collate all the data together, and then it's important to break it down to understand kind of where those risks come from. So this is the top 10 at-risk LGAs. So we've got in dark blue buildings, and then we've got kind of lighter blue land, really light blue road, and then on the kind of dashed line is the population. So you can see kind of how that split is. So unsurprising, we've got a lot of buildings at risk. Yeah, it's kind of unsurprising given that developers like to buy cheap land. Cheap land is in at flood risk areas, so that tends to happen quite a lot if planning policy isn't in there. And then you've got kind of the amount of land at risk. If you have, for example, any data from land use data, so you can download the land use maps from Geoscience Australia, you can also intersect that and you can come up with how much agricultural land's at risk. So that's kind of great for your farmers and things like that, or you can have a look at anything like that. So you've got different options in there as well. You see the greatest population at risk is really from Mora, and that comes out as well. So these are kind of statistics that we want to pull out for different communities when using this data. And like I said, most councils and humanitarian organisations, they don't have a lot of money, so we really want to harness this freely available data as much as we can. It's not all in one source, so you do have to do a little bit of digging. And finally, what you want to also have a look at is generally like changes in risk profile, because what we're looking at is one snapshot in time, and you might have nothing flooded in a 20-year event, and suddenly you'll have 10 houses flooded in a 100-year, and so you want to understand that risk profile for both communities and governments. So if you're ever doing this with kind of flood maps of any sort of type, or potentially, I don't really go into bushfires very much, potentially that as well, you can have a look at different kind of probabilities of flooding and then kind of pull that out for the community. So I'll run this little video here. So again, this is the top 10 LGAs. So this is going through each return period, so an increasingly larger flood from 20-year flood to a 1500 flood. What you notice is, for example, I think it's Murray. Murray starts out as the kind of the fourth most at-risk LGA in a 20-year flood, but by the time you get to a 1500-year, it's the second largest. So as our events get more extreme, it's going to become more and more a risk. And this is important because with climate change, obviously there's a lot of uncertainty looking into the future, but the general rule of thumb is that the larger floods are going to become more frequent. So that 1500-year event is probably going to shift closer to a 100-year. And so that's something that communities should be thinking about, that they might not be, if they are at risk in a 1500-year event, that still is something to consider, because they will be at risk for those larger events in the future, should they happen. And you can also have a look at kind of that step as well. If they suddenly have a large step to risk, then there's kind of certain infrastructure or planning that can go in to kind of reduce that or increase their resilience. So what I kind of want to get across today is, when we're generating kind of individual and combined exposure risks, so it's kind of taking all that spatial data, we require really good asset data. It doesn't have to be the best, but it does need to be kind of consistent. What we also need to do is understand any sort of biases in there. But yeah, so try not go about mixing and matching spatial data sources. When we do our global assessments, we'll use Bing Maps. When we do local, we'll try use anything generated by Australia. Every country and district will have its own spatial data source that we can go to. Asia Pacific has its own website where it's got great data, but you do have to go a little bit of data mining as well. Being able to build on the spatial maps and really take out that information and collate that for communities is a really important part of our work as spatial scientists. Because people can look at data or they'll see a map, but we really need to make sure that we're producing a map that's going to show them what they need to know, and that takes a lot of thought. And often that won't come from who you're working with, the community. It won't come from your employer. It will often come from you as the spatial analyst. So it's really good to have a think about that, bounce ideas around, create multiple maps, have a go, and really think about what's important. So for us, it's really community resilience to flooding, and so that's why we're focusing on intersecting, buildings, floods, things like that. If they're kind of more focused on how to build resilience, we might want to really intersect our flood maps with land use and try to drive places where you can build nature-based solutions, like optimize your kind of resilience there. This is the kind of starting point, these kind of large-scale assessments for prioritizing of efforts and resources. So if anyone's worked with councils, they don't generally have a lot of money. So you really need to make sure that we're giving them as much information to undertake kind of risk-informed decision-making. That is really important, not just for present day, but also for the future. And for us, kind of, free, publicly available geospatial data sets are kind of critical for us in supporting at-risk communities. So even compared in WA, it's relatively rich, but if you go up north, those councils have even less money. If you go to the Northern Territory, even less, and they won't have the ability to buy high quality data. So we need to kind of make the most of it. So thank you.